So if my weight is 1,000 newtons on Earth's surface, so I weigh 1,000 newtons on Earth's surface, we can ask the question, what is my weight a distance of one Earth radius above the Earth's surface? So here I am standing on the surface of the Earth, so my distance from the center of the Earth is r sub e, radius of the Earth, right? Where r sub e, I'll write it up here, re equals 6.37 times 10 to the 6 meters, right? If I'm raised that distance again, how much do I weigh? And we can figure that out by saying, look, the force of gravity on Earth is g times the mass of the Earth times the mass of me over the radius of the Earth squared, right? The force of gravity up here, all the numbers are the same. G times the mass of the Earth. The mass of the Earth doesn't change. The mass of me doesn't change. Remember, mass doesn't change. Weight gets different, but the mass is the measure of the stuff that I have, and that doesn't change. Divided by, and so instead of having the radius of the Earth here, I have twice the radius of the Earth, because that's my distance now, right? And so if I square that out, I get G times the mass of the Earth times the mass of me over, if I square that, it becomes 4 times the radius of the Earth squared, right? It's 2re times 2re, which is 4 times re squared. That's equal to 1/4 times g times the mass of the Earth times the mass of me over the radius of the Earth squared, right? But this thing is what we said is 1,000 newtons, right? This is just 1,000 newtons. This is what I weigh on the Earth's surface. So it's 1/4 times 1,000 newtons, which is 250 newtons. As I get farther away, my weight decreases because the gravitational force on me decreases. It decreases as 1 over r squared. So if I'm twice as far away, my weight is 1/4 as big. So here's another problem. If I weigh 1,000 newtons on Earth's surface, what would my weight be if the Earth were made more compact so that it had the same mass but half its radius? So here's me standing on the normal Earth, remember, not to scale. And now the Earth has been made more compact so that its mass is the same, but it's half the radius. So the Earth's been crushed down, right? And so on full Earth, I'll call it, we'd say, well, my weight is just g times the mass of the Earth times the mass of me. You know, I'm going to put a W for Wayne there, if I can write a good one. Over the radius of the Earth squared, right? And that's the thing that's 1,000 newtons, not 100, 1,000 newtons, right? On compact Earth, I have the force of gravity is equal to g times the mass of the Earth times the mass of me over radius of the Earth over 2 squared. Because now my distance from the center mass of the Earth is half the radius of what we call the regular Earth. And so what is that? That's so if I square that, that's g times the mass of the Earth times the mass of me over the radius of the Earth squared over 4, right? Well, if it's in the denominator of the denominator, I invert and multiply, and that comes out to a force of gravity that's equal to 4 times g times the mass of the Earth times the mass of me over the radius of the Earth squared. But the number in parentheses is just that, is 4 times 1,000 newtons, which is 4,000 newtons. So as the Earth gets more compact, my weight gets greater and greater. This is what happens to stars later in their life. Stars collapse inward as they age, and a black hole is something that's collapsing forever, but they're white dwarfs and they're neutron stars that have fixed sizes but are just much more compact. And if you were on their surface, you would experience a much higher gravity. All of the mass is there, but it's in a much smaller size. So you're just much closer to it, and so you have a much higher force of gravity, because how close you are to it is reflected in the denominator. And so when that gets small, the force gets big. So we're going to talk a little bit about satellites and Kepler's third law. So Kepler's third law said that the period squared is proportional to the cube of the semi-major axis. We're going to be talking about circular orbits. I used a lowercase r there, so I guess I'll use one here, but it doesn't matter. Anytime you have a direct proportionality, like how much you earn is proportional to how many hours you work, or how far you can go depends on how many gallons of gas was in your car, and so on. You can turn a proportionality into an equation just by inserting a constant. So we say period squared is equal to some constant times the semi-major axis cubed. And since we're talking about circles, I'll be referring to that as the radius. We won't deal with the ellipses, really. The math is just a little too sophisticated, but it's not much harder once you sort of build in the other math. We won't do that. So the period squared is equal to some constant times the radius cubed, and we're going to show this using Newton's laws. And so here's our satellite. Say it's orbiting the Earth, but it could be orbiting any planet. We'll just have it orbiting the Earth or a sun or something. It's traveling in a circular orbit with speed v at radius r from the center of the planet, right? And so we know that there's a force of gravity going this way. And this force of gravity is the centripetal force, right? It's the force that keeps the thing going in a circle, right? We also know that the satellite is accelerating this way at v squared over r, because it's moving in a circle, and we've already talked about uniform circular motion. And so the only force that's acting on this, there's no normal force, there's no tension force, the only force that's acting is gravity. And so this is really a pretty straightforward problem to analyze from a Newton's law standpoint. By the way, as a side note, it's always good to, if you're going to do like a satellite problem, put your object over here rather than up here or over here or on this side or something like that, because most of our coordinate systems look like this, and it's just, if you put the satellite there, you get to have a coordinate system that has this right up the x-axis. And so if I draw a free body diagram, you'll see it here in a second, right? All I have is this. I have the force of gravity going this way. I have an acceleration a sub c, which is v squared over r, right? And then so I only have one force. And so then I can draw my coordinate system, y and x, and that means I only have to worry about the x direction. Right? And so if I come over here, I can say, look, I can solve this problem. I can say the sum of the forces in the x direction equals m a sub x. That's equal to m a sub c. That's my centripetal acceleration, which is just mv squared over r, right? And what is that force? That force is just the force of gravity, and so it's g times the mass of the Earth times the mass of the satellite, which I'll put a little m over here just so we agree on that, over r squared is equal to mv squared over r. And so this equation has all we can say really via Newton's laws about this problem, and from it we have to get a relationship between the period and the radius, right? And you don't even see the period in here. We do see the radius, and by the way, I can just go ahead and cancel that and that. And notice I can also cancel the mass of the satellite off both sides. I should be careful while this equal sign is still there. And so once I do that, I probably want to get rid of that equal sign. And this just leaves me with g times the mass of the Earth over r is equal to v squared. And now we have to say, well, how do we relate v to the period? Well, velocity is, distance over time, at least speed is, right? And so if I wanted to write the velocity in terms of things on this orbit, You might pause this and see if you can figure that out. I'll go ahead and say it. You can look when you're ready. Right? The distance around this circle is 2 pi r, right? And the time it takes to do that is 1 period. That's what the period means. It means the time to go around once. And so the speed is 2 pi r over the period. And so I can replace that here, and I can say, look, g times the mass of the Earth over the radius is equal to 2 pi r over the period squared, right? And now you're starting to see the variables that we're looking for in here. I can say g times the mass of the Earth over the radius is equal to 4 pi squared r squared over the period squared, right? And I can cross multiply the r and cross multiply the period squared, and I get g times the mass of the Earth times the period squared. If I multiply both sides by the period squared, that's what I get on this side. And then I'm going to multiply both sides by r, and I get 4 pi squared r cubed. And now I've got a period squared and an r cubed. Now I can just divide both sides by g times the mass of the Earth, and I get the period squared is equal to 4 pi squared over g times the mass of the Earth times the radius cubed. And this thing is my constant that I talked about up there, right? 4 pi g and the mass of the Earth are the same for anything that's orbiting the Earth, right? These things are constants, they don't change. So if you're orbiting the Earth, this will be the constant for you. And no matter what your orbit is, whether you're in a low Earth orbit or you're the moon orbiting the Earth, the square of your period is going to be that times the cube of your orbital radius. Same thing with all the objects orbiting the sun, and that's what Kepler did. Kepler looked at the period of Mercury and found that it was that the relationship between it and the cube of its orbital radius was this factor. He just found out what the number was, and he found out this number was the same for Saturn, Jupiter. They didn't know about Pluto in Kepler's time. Saturn, Jupiter, Venus, Earth, and Mars. And so if you tell me what the radius of the orbit is, I can tell you what its period is. Right? Same thing here. If you give me the speed of a satellite in a circular orbit, I can tell you what its radius is. And so I'll do an example or two of that. So here's just another satellite problem. Hopefully, once you've seen one or two of these, you'll see that almost all the satellite problems are kind of look the same. This is a satellite that orbits 630 kilometers above the Earth's surface. So this black line is the Earth, right? And I'm trying to make this to scale. 630 kilometers is about 400 miles or something like that, right? The Earth's radius is 4,000 miles. And so this is a satellite that's very near the surface of the Earth. This might be the space station, say. It's up, but it's not just way away from the Earth. Maybe I'll do one more example with something that's much farther away. It'll look just like this problem, except the picture will be different. And so here's my satellite. The force of gravity is the same thing, or the centripetal force is the force of gravity, vice versa. The centripetal acceleration is v squared divided by r. Again, r is the distance from the center of the Earth to the path of the satellite, right? We're assuming these are all circular orbits. And so when I draw the free body diagram, it looks just like the last free body diagram we drew for a satellite. I was careful to put it on the left side so that my satellite is, the force of gravity is right up the x-axis. There's my centripetal acceleration. If I want, I can say that's v squared over r, right? And so I've got a complete free body diagram. It's very simple, and I can just jump over here and say the sum of the forces in the x direction equals ma sub x. That's equal to m times a sub c, which is m times v squared over r, right? And that force is just this force, and so that's the force of gravity, which is just g times the mass of the Earth times the mass of the satellite over r squared, same r, the distance from the center of the Earth to the satellite, is equal to mv squared over r, and just like in the last problem, the m's go away. Any satellite with this velocity will stay in orbit. The only real assumption is that these masses are small compared to the mass of the Earth. Jupiter won't orbit the Earth, it would be the other way around. And so as long as these are small masses compared to the planet, all this is fine. I can cancel that r and one of those r's, and I get g times the mass of the Earth over r is equal to v squared. And just like last time, we're looking for the period, right? This is t. And so just like last time, we recognize that the speed is 2 pi r over the period. That is to say, the speed is just distance over time. The distance is 2 pi r, and the time is a period. And so we're really just doing the same derivation we did last time. G times the mass of the Earth over the radius is equal to 2 pi r over the period squared. And if you do the same sort of math to that and solve it, you square this side, you get, this is 4 pi squared r squared over the period squared. And so you look at these two guys and you cross multiply and divide, and you get the period squared is equal to 4 pi squared over g times mass of the Earth times r cubed, or the period is equal to the square root of that mess, 4 pi squared over g times the mass of the Earth, r cubed. Right? And so if we want to write all that out, give myself a little more space, 4 pi squared. So what is this r, right? Well, r is just the radius of the Earth plus 630 kilometers. Right? That 630 kilometers is this distance. That's 6.3 times 10 to the 5th meters, right? And so the radius of the Earth is 6.37 times 10 to the 6th meters plus 6.3 times 10 to the 5th meters is equal to I'll write it here. R is equal to 7 times 10 to the 6th meters. If you work that out, and so because this here up to the surface of the Earth is RE, and that's what this number is, right? RE equals 6.3 times 10 to the 6th meters. That's the radius of the Earth. That you'll see that a lot. Hopefully you already have, right? So this is 7 times 10 to the 6th meters to the 3rd power. And the denominator is g, which is 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. Am I still on screen? Barely. And then the other thing I need in this denominator is the mass of the Earth, which is 6 times 10 to the 24th kilograms. I guess I've got to erase my free body diagram a little bit at this point. And if I evaluate this, I get 58.17 seconds, or 1 hour and 37 minutes. So this is roughly the orbit of the space station, and what all this says is it takes about an hour and a half to go, a little over an hour and a half to go around the Earth one time. So its orbit of the Earth is pretty quick, right? Imagine traveling all the way around the Earth in an hour and a half. Right? So then I can ask a few other questions, like I can say, that's the period. I can say, what is its speed, right? And we could have calculated that earlier because we had this equation. We had g times the mass of the Earth divided by the radius is equal to v squared, or you could just say v is equal to the square root of g times the mass of the Earth divided by the radius. which is the square root of 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times 6 times 10 to the 24th kilograms all over, that's all going to be inside my square root, 7 times 10 to the 6th meters, like that, right? And so what I got for that was 7.561 meters per second, or 7.56 kilometers per second, which is about 4.7 miles per second. So it's zipping right along, right? That's its speed. You could also you could also say, once you had the period, you could also say, equals 2 pi r divided by the period, which is 2 pi times 7 times 10 to the 6 meters divided by 5.817 seconds, which should give you essentially the same number. Another interesting question you can ask, that covers that one, I guess, is what is g at the space station? Remember, we evaluated g and we said g is equal to g times the mass of the Earth divided by the radius. Well, normally we have the radius of the Earth, but here we can just evaluate the local acceleration of gravity. Sorry, it's going to be squared. Over by instead of using the radius of the Earth, they're using whatever distance you're at, right? And so this would be 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times 6 times 10 to the 24th kilograms all over 7 times 10 to the 6th meters squared. And what I get for this is g is equal to 8.17 meters per second squared. And the reason this is kind of interesting is that that's not a whole lot lower than it is on Earth, right? The gravity on Earth is 9.8 meters per second squared, and this is up a good bit, but it's not zero. And yet, when you see people on the space station, they're floating. They call it zero gravity, right? And so you might ask, well, why is that happening if gravity still exists up there? And the answer is because they're falling, right? They're falling just as if you just drop them. You just pick them up and drop them. If I push you off a cliff, you won't feel, you'll feel weightless, right? But you would be accelerating as you were falling downward, right? Until you hit terminal velocity, but let's neglect that, right? You'd be accelerating. These people are accelerating just as surely as if they've been dropped, but they're moving so fast horizontally that they don't fall into the Earth. And so the reason they feel weightless isn't because there's no gravity, which they often say. It's because they're free falling under the influence of gravity. And anybody who's free falling feels weightless.